Hi, everyone. So today we're going to be moving on to the area problem. And that's the start of integral calculus. But before we do that, we need to finish what we did last time and prove these antiderivatives of the common trig functions. Okay, so this is what we wrote last time. Okay, so we're going to be proving these today. Okay, so these first two here, cos x and sin x, you don't really need to prove them. We can take them as given. However, the third and the fourth one, we need to prove that. Okay, you won't need to prove it in any test or tutorial test, but it's good to have some practice on showing that these are true. Okay, so let's start off with the antiderivative of sec squared of x. Okay, so if we're given the function sec squared of x, then we need to show that the antiderivative, capital F of x, is given by tan of x plus c. Okay, so how do we prove that this is the antiderivative? Well, we need to show that the derivative of capital F, the derivative of tan, gives us sec squared of x. Okay, we want to show this going backwards. So we start off with capital F. So capital F of x is equal to tan x. We need to show that this derivative gives us sec squared of x. Okay, so f prime of x is equal to d by dx of tan x, which is d by dx of sine x over cosine x. Okay, so now we've got this quotient or fraction here with a function on the top and a function at the bottom. So we need that quotient rule from differential calculus. I'm just going to write that on the side here so we can see what it is. So d by dx of f over g is given by g f prime minus f g prime, so we swap them around, over g squared. Okay, so we need to use that over here. Okay, so let's do that. So firstly, g, that's the bottom function, so that's going to be cos. So we're going to have cos x times f prime, that's the derivative of the top. The derivative of sine is cosine, so we have cosine x, minus, at the top here, we've got f, that's going to be sine. And then g prime, the derivative of cos is going to be minus sine. Okay, all divided by g squared. In this case, g is cos of x. So that's going to be cos squared of x. Okay, so in the top, we're going to have cos squared of x, multiplying those two together. Then sine of x times sine of x is going to be sine squared. And then the minus and the minus is going to make a plus. So we have plus sine squared of x, and still divided by cos squared of x. Okay, so that's a nice trig identity at the top. Cos squared plus sine squared, that's going to be 1 divided by cos squared of x. Now, another identity is that sec of x is 1 over cos x. And just for completeness, let's put the other one. Cosec of x is 1 over sine x. Okay, so those reciprocals. But we just need the top one. So if 1 over cos is sec of x, then 1 over cos squared, that's going to be sec squared of x. Okay, which is exactly what we wanted to show. We wanted to show that the antiderivative of sec squared is tan. Okay, and we showed that by going backwards because the derivative of tan is sec squared. Okay, so we've shown that. Now we need to show the other one. We need to show that the antiderivative of sec x tan x is sec x. So how do we show that? Well, we go backwards. We need to show that the derivative of sec x is going to be sec x tan x. Okay, if we can show that derivative, then that means this right-hand side here must be the antiderivative. Okay, so let's do that over here. So proving that if f of x is equal to sec x tan x, then capital F of x, the antiderivative, if we take a look here, is going to be sec x. Okay, so how do we prove that? Well, again, we're going to start off with the right-hand side here, take the derivative, and we should get to the left-hand side. So f of x is equal to sec x. We need to find the derivative and show that that is equal to sec x tan x. So f prime of x is equal to d by dx of sec x. Okay, but remember, sec x is 1 over cos x. So that's d by dx, 1 over cos x. Now, you could use the quotient rule for this, but what I'm going to do is just write this as d by dx of cos x to the minus 1. Okay, so now I can use the chain rule because we've got this outside function of raising to the power minus 1, and we've got this inside function of cos x. So this is going to be minus cos x to the minus 2 times, and then the derivative of cos is minus sine. Okay, so we've got that. Let's try and simplify this. Sorry. So the first thing that we have here is that these two minus signs are going to cancel. And cos x to the minus 2, we can take that down to the denominator. So we're left with sine x over cos squared x. Okay, now this doesn't look like sec x times tan x, but with a little bit of manipulation, we can get there. So we can write this as sine x over cos x times 1 over cos x. Okay, I've just split up the cos squared in the denominator. Now this first term here, sine x over cos x, that's tan x. And then 1 over cos x, we know that already, that's going to be sec x. And if you really want to show that that's a sec x tan x, let's just flip this around, sec x tan x. That doesn't make any difference, but over here we wrote it as sec x tan x over there. Okay, so then that proves that the antiderivative of sec x tan x is sec x. And we're going to be using that quite a bit later on. Okay, so with that done, let's move on to the main topic for this lecture, and that is the area problem. Okay, so firstly, what is the area problem? Okay, so the area problem is basically given some function of x, so we have x and y, any function like that, f. What we want to do is find the area below the function and above the x-axis between some endpoints here. Let's say that's A and that's B. Okay, so this area here that I'm coloring in, what is that area? Okay, so how do we go about finding that? Well, just by looking at this, there's no formula for finding it. So we know how to find the area of rectangles, circles, triangles, and so on. But this curve over here, this f function curve, that makes it very difficult to find the area. So what we're going to do is, firstly, we're going to approximate the area. Okay, in this case, we're going to be using rectangles because we know the area of a rectangle. So we're going to approximate the area using rectangles. And then we'll see that if we make these rectangles very, very thin, okay, or another way of thinking of that is putting lots and lots of rectangles between A and B, we get a better and better approximation. So the idea is, if we take the limit of infinitely many rectangles, then we're going to get the exact area. Okay, so let's start off with the approximation. So I'm just going to draw in a couple rectangles to show you how these rectangles approximate the area. So our first rectangle can go here, then the second one like so. So I'm just filling in all the rectangles here. So the idea is we have n rectangles. So we have 1, 2, 3, 4, 5, 6, 7 rectangles here, each with a constant width going along from A to B. And the height of the rectangle, the height, is given by the function value at that point. So here at point A, there we go, at point A, we've got a rectangle with a certain width. Let's call that width delta x, and a certain height f of x, and that is given by this value at A. So this height here would be f of A. And we do the same going along there. So if we sum up these areas, so this has a certain area. If we sum up the areas, we get an approximation to the exact area that we have in blue there. So we can write that the area is approximately equal to the sum of the nth rectangle's height. So let's say this one is rectangle number R. So the nth rectangle's height times delta x. Okay, because the area is base times height. Okay, and then that gives us an approximation to the area. Now I'm going to draw the same picture, but this time I'm going to use more rectangles, and we will see that the approximation gets better. Okay, so we have the same sort of function here, the same interval from A to B. Okay, but now I'm going to use smaller rectangles. Or another way of thinking of that is using more rectangles. So we just squish them in. So let's draw that in. So if I use much smaller rectangles like this, okay, dot, 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 just continue this process. Okay, we see that this error amount, you see where the rectangles stick out over there? This error amount over here is going to get smaller and smaller the more rectangles we have. Okay, so more rectangles, or in other words, thinner rectangles, give a better approximation. to the exact area that we're trying to find. Okay, so this is the idea that we have. Okay, so so far we're just thinking about this. Now we need to formalize this so that we can actually do some calculations. Okay, so how do we formalize this? So firstly, let's define what the width of the rectangles are going to be. So we want to formalize this. So let's define the width. Okay, so we've got an interval from A to B. So the width of the interval is going to be B minus A. That's going to be the length of the interval. If we are going to try and fit in n rectangles, then that means the width of each rectangle, remember we call that delta x, is going to be B minus A divided by n. So B minus A, that is the width of the interval. And n, that is the number of rectangles. Okay, so width of the interval divided by number of rectangles, that gives us the width of a single rectangle. Okay, what about the height? Well, we said that the height is going to be the function value at that point. So that's going to be f of xr. Okay, but how do we get this xr? Where does this come from? Well, if we go back to our picture here, we start at A. So at x equals A, we start there. And we are going to hop along until we get to B. And each hop from one rectangle to another is a hop of width delta x, because each rectangle is delta x wide. So that means the x position of the rth rectangle is going to be our starting position, plus however many hops we're going to take, delta x. Okay, so if I is equal to 0, we start at A. If I is equal to 1, we have A plus delta x, which is the next rectangle, and so on. Okay, so what is the approximate area going to be? So the approximate area is equal to the sum I equals 1 to n f of xr delta x. Okay, so this is the first important formula that we need to know. Okay, so now I need to point out a little bit of a technicality here. But over here, we chose that the height of the rectangle is the function value at xr. In other words, if I draw a little picture again, say we've got our function like this, and we've got a rectangle here, and then another one here. So at A, we take this to be the height. In other words, at the start of the rectangle. However, we could also choose the other end of the rectangle. We could choose this point to give us the height of the rectangle. So here would be A plus delta x. Okay, so in this case, we could use the left end point. So here is the left end point. Okay, because we're using the left side of the rectangle. Or we could use this, and this would be the right endpoint. Or in fact, we can use any point between the left endpoint and the right endpoint. No one says that we can't use the point in the middle. So let's just make a little note here. So we could use any point. Yeah, we call this a random sample point. Yeah, so currently, if we have this finite sum over here, then it does matter which point we use. If we use the left endpoint, we're going to get some answer. If we use the right endpoint, we're going to get a slightly different answer. And if we use a random sample point anywhere between the left endpoint and the right endpoint, again, we're going to get a different answer. However, the nice thing is the choice doesn't matter. So the choice doesn't matter if we take n to infinity. Okay, so again, this is just the idea that we have. So let's put a cloud around that. That's just us thinking. So we have this idea that the choice shouldn't matter if we take n to infinity. Because if we do smaller and smaller rectangles, it shouldn't matter where we pick the x value that gives us the function value, which will then give us the height of the rectangle. Okay, so that's the idea that we have. But in fact, we flip this around. So we say that the limit, because remember, we want to take n to infinity, so we're going to have to take a limit at some point. We say that the limit exists. Okay, so the limits exist. We know that from a previous math course. We say that the limits exist if the result doesn't depend on the choice of sample points. Okay, and again, this is just more thinking here. So as we take n to infinity, we say that this limit, the limit of taking n to infinity, remember that that's a limit there. We say that the limit exists if the result doesn't depend on the choice of sample points. So if we're given some kind of function where the area does depend on the choice of sample points, well, then we say that the limit doesn't exist. Okay, because we don't get a fixed result in the end that doesn't depend on the points. So the limit doesn't exist. Okay, so more specifically, what is this limit here? So remember, we want to take the limit as n goes to infinity. So we write down that the exact area is equal to the limit as n goes to infinity of the sum I equals 1 to n. Sorry, I equals 1 to n f of x r delta x. Okay, so we took the limit there. Okay, and this limit needs to exist. So technically, we should be looking at all possible sample points. But later on, we will see that, in fact, that doesn't really matter. You can prove it doesn't matter. And so we can just use this one. We can choose a selection of sample points and then use that to find the area. Okay, so a little bit of terminology now. Okay, so the sum that we had at the beginning, so the sum from r equals 1 to n, f of xr delta x is called a Riemann sum. Okay, named after the mathematician Riemann. Okay, so that's called a Riemann sum. And if we take the limit, so the limit as n goes to infinity of the Riemann sum, so I equals 1 to n, f of xr delta x. So if we take the limit, then this is called a Riemann integral. Again, named after Riemann. So if we take the finite sum to approximate the area, then that's called a Riemann sum. If we then take the limit as n goes to infinity, which remember, we came up with that idea to turn the approximation into an exact area, we then call that a Riemann integral. And we will look at some examples of calculating these Riemann integrals. Okay, and then just a bit of notation. So instead of writing this limit and sum all the time, we replace this with a little bit of notation. We draw this curly S shape, okay, the S standing for sum, because it's a sum. We put an A at the bottom to show that that is the start of the interval. We put a B at the top to show that that's the end of the interval. Then we put the function in the middle, and we write dx. So this delta x that we had before now becomes a dx, much like how in differential calculus, you had delta y over delta x, okay, as your average gradient, and then that became dx by dy. Oh, sorry, dy by dx, sorry. So in differential calculus, you had delta y over delta x, and then that became dy over dx in the differential calculus. Here, we take the same inspiration, delta x then becomes dx. Okay, same kind of idea. When we take the limit, the deltas turn into d's. Okay, so this is just a complicated symbol, but what it represents is the limit as n goes to infinity of the sum from I equals 1 to n, f of xr delta x. So instead of writing the limit and the sum and all of that, we just replace it with one bit of notation here. And it holds all the same information. Okay. And again, that we call the Riemann integral as well. It's just another way of writing the Riemann integral. Yeah, but another way of saying it, this notation here in blue, we call a definite integral. Okay, so the reason we call it a definite integral is because this type of integral gives us a definite value, gives us the area under the curve. So definite integral gives us a definite result. In this case, the area under the curve. Okay, so this thing in blue, we call that a definite integral. Now, we're not going to get to this now. We'll take a look at this later. But we also get something called an indefinite integral. And I'm sure you can see here, if this is a definite integral with a definite result, then an indefinite integral will give us something like an indefinite result. That doesn't make too much sense now, but we will see later on. This gives us an indefinite result. Okay, but that's just a bit more terminology for this. Okay, what we want to do now is look at an example. So we want to find the area under a curve using this Riemann integral. Okay, so example. Find the area under f of x is equal to x squared between x is equal to 1. So that is the lower bound of the interval. And x is equal to 3. Remember, that is the upper bound of the interval. Okay, so what do we do? Well, there's a number of things that we have to do before we can get to the main calculation. So step 1 is to find delta x, which is the width of our rectangle. So delta x, remember that is b minus a over n. So that's going to be 3 minus 1 over n. That's going to be 2 over n. Okay, good. Next, we need xr. Remember that was our sample point for the rth rectangle. Okay, now we'll get to this in the next lecture, but remember what I said, it shouldn't matter what the sample point is. So let's just take the sample point to be a plus r delta x. Okay, so technically speaking, you should prove that this works for any choice of sample points, but you can just take it as we know it works for any sample points. So let's just use this one. Okay, so the lower bound a, that's going to be 1 plus r, and then delta x, we know that is 2 over n. Okay, so that's xr. That is our sample point. What about the height? So that's going to be f of xr. That's going to be f of 1 plus 2I over n. But remember, what was f? That was x squared. So that is going to be 1 plus 2I over n, all of that squared. Okay, so that's just a binomial expansion there. That's going to be 1 plus 4I over n plus 4r squared over n squared. Okay, so we've got all the pieces now. Let's put it all together to find the area. So the area, remember, in terms of the limit of the sum, so that's going to be the limit as n goes to infinity of the sum as I goes from 1 to n of the area that was base times height. So that's f of xr for the height, delta x for the base. Okay, so we calculated all of these things already. So let's just substitute. So that's going to be the limit as n goes to infinity, the sum from I equals 1 to n. F of xr, that's going to be 1 plus 4I over n plus 4r squared over n squared. And then delta x, that was 2 over n. Okay, so now we just need to calculate the sum first. And then once we've calculated the sum, we then take the limit. And then whatever's left over after the limit, that is our answer. So this is going to be the limit as n goes to infinity of the sum from I equals 1 to n Let's distribute the 2 over n into our sum. So we're going to have 2 over n plus 8i over n squared plus 8r squared over n cubed. Okay, so that's just distributing that inside. Okay, so now we can separate this because we've got a sum of individual terms. We can split that into individual sums and see what we get. So that's equal to the limit as n goes to infinity. Okay, now I'm going to distribute the sum or split the sum up into different parts. Okay, so we're going to have 2 over n. The sum from I equals 1 to n of just 1. Okay, because remember 2 over n doesn't depend on I, so we can take that out. We can do the same for the other terms. So we're going to have plus 8 over n squared. The sum from I equals 1 to n of r. Plus, same thing for the third term, 8 over n cubed. The sum from I equals 1 to n of r squared. Now these we can calculate. So we know that. We know how to do this sum. And we know how to do this sum. Okay, remember there are formulae for each of these sums. So let's just plug those in. So we have the limit as n goes to infinity, 2 over n times the sum from 1 to n of 1 is just 1 plus 1 plus 1 plus 1 all the way up to n. So that is just going to give us n plus 8 over n squared. The sum from 1 to n of I is 1 plus 2 plus 3 plus 4, dot, 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 all the way up to n. There's a nice formula for that. That's going to be n plus 1 over 2 plus 8 over n cubed. Okay. And then the sum of r squared. So that's 1 squared plus 2 squared plus 3 squared, all the way up to n squared. There's a nice formula for that. And that's going to be n plus 1, 2n plus 1, all over 6. So let me just highlight what we added here. So that's going to give us n. The second sum gives us n times n plus 1 over 2. And the third sum gives us n plus 1, 2n plus 1 over 6. Okay, you don't need to show that these are true. You just need to know how you get from the sums to the closed form expressions in this bottom line. Okay, so now we've got a bit of algebra to do to clean this up, and then we can take the limit. So this is going to be the limit as n goes to infinity, 2 over n times n, that's just going to be 2, plus we have 8 over n squared, but there's another 2 in the denominator. So 8 over 2, that's going to become 4 over n squared. And then n times n plus 1, that's going to be n squared plus n. Plus 8 over 6, we can divide top and bottom by 2. So that gives us 4 over 3n cubed. And then at the top, we still have an n. And then, sorry, multiplying out the brackets, we're going to get 3n squared plus n plus 2n, so that's plus 3n, and then plus 1. Sorry, not 3n squared, sorry, that's a 2n squared. Yeah, so 2n squared plus n plus 2n, so that's plus 3n, and then plus 1. Okay, so a bit more work that needs to be done. So this is going to be the limits as n goes to infinity of 2 plus 4 divided by n squared times n squared. Well, that's just going to be 4 plus 4 over n squared times n. That's going to be 4 over n plus this next one is going to be 4n over n cubed times 2n squared. So that's going to be 8 over 3. And then the top will be an n cubed. The bottom will be an n cubed. That cancels. Next, we have 4n times 3n. So that's going to be 12n squared. So 12n squared. But we're dividing by 3n cubed. So that's a 3n at the bottom. Plus, the last one is just multiplying by 1. So we just have 4n over 3n cubed. So that leaves us with an n squared at the bottom. Okay, so now we can finally take the limit and see what happens. So just a little note with taking this limit, all of the terms that look something like this, and this, and this, they are going to go to 0 because we are dividing by n, and as n gets bigger and bigger and bigger, the fraction will get smaller and smaller and smaller. So as the limit, as n goes to infinity, the fraction will then go to 0. So all of them go to 0. So that one goes to 0, this one goes to 0, and this one goes to 0. Okay, so we've taken the limit. What is left over? So the leftover is going to be 2 plus 4 plus 8 over 3. Okay, and we can add these up, and we're going to get 26 over 3. So this is the exact area. So this is the exact area below f of x is equal to x squared from x equals 1 to x equals 3. Okay, so that's the area below the curve. Okay, so it looks like a very long calculation, but each step is not so bad. So let's just run through this again. So the first thing that we had to do was calculate the width of the rectangle. So that's the delta x. It's always going to be b minus a over n. You just plug in what you know, and you can simplify that. Okay. The second thing that we need to do is calculate the sample point. So that's our xr. Remember, you can take any sample point. So in this case, we take a plus r delta x. I recommend that you use this one as well. Okay, again, you plug in what you know. We know what a is. We know what delta x is. We calculated that before. So we can calculate xr. Okay, the third thing that we need to do is calculate the height of the rectangle. So that is f evaluated at the sample point that we just calculated. So that goes down here. So we can see step 2 needs step 1 and step 3 needs step 2. So you must be very careful with these first 3 steps. If you make a mistake on step 1, you see how that carries down to all of the other steps. And that's going to be really bad. Okay, step 4 is just writing out this definition here. So we know that the area calculated using a Riemann integral is going to be the limit as n goes to infinity of the Riemann sum, which is the sum from 1 to n, f of xr, the height of the rectangle, delta x, the width of the rectangle. Okay, so we just simplify that. Then in step 5, we separate out the sums. So we had the sum of individual terms being added, and we replaced that with these individual sums that we have in yellow. The reason we do that is because each of these individual sums, this one, and this one, can be replaced with their closed form expressions. For example, we know that the sum of r from 1 to n can be replaced with n times n plus 1 over 2. We can do that replacement. The same thing with the sum of 1, the sum of r squared, or if you're given the sum of r cubed, you can replace that as well. Okay, so we remove all of the summations. We just left with some long expression with only n's, like that. So we clean that up as much as we can. And then we're going to end up with something like this last line over here, with a bunch of numbers and some expressions with either n or n squared or n cubed in the denominator. The important thing is that this is in the denominator, there, and there. Okay, so why is that important? Well, for our next step, step 6, over here, when we take the limit, all of the terms with n or n squared or n cubed in the denominator, they will go to 0. Okay, like I said before, imagine it like a fraction with n being in the denominator. If n gets bigger and bigger and bigger, then the fraction gets smaller and smaller and smaller. So in the limit, as n goes to infinity, the fraction goes to 0. So these three fractions all go to 0. And lastly, step 7, whatever is left over, we just add up. There should be no n terms remaining. If you have any n terms remaining, you've done something wrong in the previous step. So you see here, we took the limit as n goes to infinity, and the result had no n terms, okay, which is good. We add them up, we get our final answer. And remember that this is the exact area below the function. Okay, let me give you some homework to do, and then we will check the homework later on when we go through the next lecture. Okay, so just some homework questions here. They're not too bad. It's exactly the same as what we covered before. So, number 1, f of x is equal to 2x minus 1 on the interval 1, 2. So we want to find the area below this curve on this interval. Number 2, f of x is equal to x squared on the interval 0, 1. And lastly, f of x is equal to 2x on the interval minus 1, 1. Okay, so that's all the homework for today. We will carry on next time with the idea of negative areas and what that means. So just a little example on that. So far we looked at areas like this, where the area is above the x-axis, so we can calculate that. However, there are cases when the area goes below the x-axis, something like this. So at the top, we have something called positive area. We'll see exactly what that means. So here and here, we call that positive area. And then anything below, we call that negative area. So here, this is positive area. And here, this is positive area. And this below is negative area. Okay, so the reason we call that below part negative area is because what is the height of these rectangles that we draw here? So if we draw a rectangle, we see that the height corresponds to the function value, right? So if the function value is negative, then this gives us a negative height. And if the height is negative, well, then the area is negative as well. Okay, we get something called the negative area. So if we want to find the area from, let's say, A to B, then the positive area parts in red will add to the area, and these negative area parts in blue will then subtract from the area. So altogether, we get something called the net area. So there we look at the positive area contribution minus the negative area contribution. We get something called the net area. Okay, we will look at this more in depth next time. Yeah, and then after that, we will look at the definite integrals. Remember, that was the integral from a to b f of x dx. That was just the notation we used for the limit of the Riemann sum. We called this the definite integral. And we will see that because this definite integral is defined in terms of sums, it has some very nice properties that come from that. Okay, and that's what we will be looking at next time. Okay, if you have any questions, please let me know on the WhatsApp group. So you're always free to ask questions there, and you're also free to email me whenever you like. Okay, I'll see you all next time.